All right, so um, sometimes this lesson kind of seems like it's separate from everything else we've been talking about when we talk about all these global things, all these things like that. But heat capacity, specific heat capacity, and then obviously when we talk about latent heat, okay, do relate to how much energy gets absorbed and how much temperature in an area changes. Right? So heat capacity is the degree to which any substance can absorb thermal energy without changing its temperature. Right? Some things can absorb very little heat before their temperature changes. Like for example, if you pick up a coin off the sidewalk when it's really, really cold, you put it in your hand, it feels cold, but only feels cold for maybe 30 seconds to a minute before it's pretty much the same temperature as your hand. All right? And that's because most metals have a very low specific heat capacity. That is, they absorb energy and change temperature very quickly. Right? Water is the opposite. Water has a very high heat capacity. That means that it can absorb a lot of energy, but not change temperature very much. And the reverse is also true. It can lose a lot of energy, but not change its temperature very much. Okay? Now, that has a pretty big influence on climate. If you recall, one of the factors affecting climate was how close to an ocean you are. Okay? Well, the ocean's water. Water has a high heat capacity, so even though the air around the ocean may change temperature, okay, the ocean will allow, well, heat will just naturally transfer. It doesn't allow, it just naturally transfers from the water to the air. The air will warm up because the air has a lower heat capacity than the water, okay? But the water, even though it's lost energy, doesn't change its temperature a whole lot. Okay? And so that's why being close to the ocean can regulate your temperature and thus affect your climate. It's because of the high heat capacity that water has. Right? Rocks and things like that typically have low heat capacities, which means if the sun shines on them, they get hot. Okay? Their temperature goes up very, very quickly. Right? Sun shines on a lake, okay? The lake's temperature doesn't change very much. Okay? It'll still be cool. Right? Or you're like you're on the beach. Okay, if you're on the beach, by the middle of the day, you can barely walk on the sand, but the water's still cool. Okay, and that's because the water has a much higher heat capacity. It's absorbing the same amount of energy as the sand, okay, but its temperature isn't changing very much. Right, and that's why latent heat and the presence of oceans can really influence the climate of an area because it has this ability to hold temperature. Okay? All right, so like we said, heat capacity is the amount of heat required to raise the temperature of an object by 1 degree Celsius. An object may be made of more than one material. Okay, so heat capacity is just I want to heat up this, I don't know, I can't even think of something right off the top of my head here, but I want to heat up this object. It's a hat or it's whatever. Okay, so I put on a hat. Well, a hat's made of a bunch of different things. Okay, the hat warms up. The heat capacity of the hat is this much. Okay, specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So it is called specific heat capacity because it is much more specific. It is this much. It is this much temperature, and it is only one specific substance. Okay? We're not talking about a hat anymore. Okay, when we talk about the heat capacity of a hat, we're talking about the whole hat and all the stuff that it's made out of. Okay, if we were talking about, let's say, just the like sizing part of it, maybe it's a small metal clip or something like that. Okay, that would be now the specific heat capacity of that small metal clip. Okay, how much energy does it take to heat 1 gram of that material by 1 degree Celsius? Okay, and there's a formula for doing that. You'll like it. It's super easy to use because everything is just multiplied together. All right, so if I want to calculate the amount of energy needed to heat something up, I would need to know how much of that substance I have, okay, and how much I want to change its temperature by, and what substance am I dealing with? Because all substances have different specific heat capacities. Okay? Each and every substance is slightly different. That's one of their physical properties. Not one of the physical properties we tested back in September, but it is a characteristic physical property of each material. All right, so in this formula, E is the energy in joules. M is the mass in grams. Okay, this is a chemistry thing, so we're back to grams. Okay, it's not a physics thing where we use kilograms. Delta T, what does delta mean? Change. Big T is temperature. Okay, little t is time, big T is temperature. Okay, and then C here, C is the specific heat capacity of the material. Right? Specific heat capacity is measured in joules per gram degree Celsius. How many joules to change the temperature of 1 gram by 1 degree? Okay, that's where joules per gram degree Celsius comes from. All right, if I want to manipulate this formula to solve for M, what do I do? Nope, I want to leave M where it is. I want to isolate M. Yeah, I just divide the C and delta T over to this side. Okay, very simple to manipulate. Just remember that it's got to be kind of like the bottoms in brackets. Don't just type it into your calculator in order, or it'll do it from left to right. We want to divide the energy by the entire bottom. Okay. All right, so it's really easy to use this formula, guys. All you got to do is isolate whatever you want, divide the other two things over to the other side. Okay, simple as that. All right, so questions on that? How that works? All right, write this one down, and then we'll go through it together here in a second. Okay, let's go over this one. Oh, I was recording that whole time. Okay, there'll be a big blank spot in the middle there. Okay, so what we have here, guys, is we want to calculate how much energy, so we're looking for E, okay, is needed to raise the temperature of 150 grams, so they gave us the mass, of water, okay, and water's specific heat capacity is 4.2 joules per gram degree Celsius, okay? Okay, so what that means is, if I want to take 1 gram of water okay? And that's a pretty small amount. It would be about the volume of a raisin, okay? Something like that. It'd be about 1 milliliter, sorry, okay? It's going to take 4.2 joules worth of energy to change the temperature of that much water by only 1 degree Celsius. Okay, that is a very high specific heat capacity. I know 4.2 doesn't look like a big number, okay, but it is. Most heat capacities are small numbers. For most metals, they're decimals. Okay, they're like 0.2 or 0.9. Okay, they're very, very small by comparison. All right, and we want to change the temperature of it from 5 degrees to 85 degrees. So what's our temperature change? 80. All right. All right, so I've got M, C, and delta T. I'm looking for E. I don't even have to manipulate it. I just need to plug in my numbers. All right, so that'll be 150 grams times 4.2 times 80. All right, so that's going to take 50,400 joules worth of energy. Is that a lot? Yes. Okay, that's why your stove is one of the biggest electrical draws in your house. Okay, it takes a lot of energy to cook food because a lot of what's in your food is water. Okay, or even if you're just boiling water, okay, if you're making coffee or making tea or whatever, okay, it takes a lot of energy to boil water to get it to that temperature. Well, yeah, and if you have an electric hot water tank, it's worse. Like I got talked into one on our last house. It's, oh no, you totally want an electric hot water tank. It's way more efficient, you know, blah blah blah. I'm like, I don't think so, but all right, whatever. Wow, huge mistake. Okay, that thing just sucked energy like crazy. Okay, just, I mean, yeah, I could get the water hot fast. Okay, but it took a lot of energy to do it. Okay, switched over to a gas one. My gas went up a little. My electricity went down a lot. Okay, so it's something to consider there. But yeah, it takes a lot of energy to heat water. All right, write this one down. Give it a try, and then I'm going to go over it with you in a minute or two here. Okay, so if you go to the second page here, right, we got the heat capacities of essentially the stuff that we'll need in this unit. Okay, and they're in alphabetical order. Okay, so in this question, they want us to figure out what material this cup is made out of. Now, what thing am I probably going to have to solve for if I'm looking for a specific material? Right, the specific heat capacity. Okay, the question gives me the mass of the cup. It's 100 grams. Okay, it tells me that it takes 4,200 joules, okay, worth of energy to raise its temperature from 12 degrees to 62, which is a temperature change of 50 degrees Celsius. All right, so I've got those two things, and or those three things, sorry, and I'm looking for the specific heat capacity. So I'll take E equals mc delta T, okay, and I'm going to solve for C by dividing m times delta T over to the other side, remembering that that's kind of got to be in brackets on the other side. Right, so I'll have my 4,200 joules, okay, divided by 100 times 50. Okay, so I'm looking at a specific heat capacity here of 0.84 joules per gram degree Celsius. Okay, that's the specific heat capacity. So I'm going to look at my table here and see if I've got anything around 0.84. Okay, here's 0.84, and it's glass. All right, so this is a glass cup. All right, that sort of makes sense to everybody? All right. Okay, try this one. We're looking for this time the final temperature. Okay, the final temperature of a 185 gram block of iron that's initially at 7 degrees Celsius if it's heated with 200 joules worth of energy. So this one has like one extra step at the end that I think you'll figure out. Okay, so let's quickly look at this one here. So in this one, they want to know the final temperature of the material of the iron block. So what am I probably solving for first? Well, I can't solve for temperature final using this formula. I can only solve for change in temperature. But they do tell me the initial, right? So I can solve for delta T, and then whatever that is, what I take it and do what with it? Add it to 7. Okay, and then I'll have it. So, right, it's going to take, so we've got 200 joules worth of energy, so E equals 200 joules. Okay, we know the mass is 185 grams, and we know that the initial temperature is 7 degrees Celsius, and we also know it's iron, which means its specific heat capacity is 0.460. All right, so I'm going to manipulate for delta T by dividing both sides by m times C. So that'll be 200 joules divided by 185 times 0.46. All right, so we're looking at the temperature changes by 2.35 degrees. So if we add that to the temperature we had initially, we get 9.35 degrees Celsius as the final temperature of the iron block. Okay. All right, so we'll work a little bit more on that tomorrow, but tomorrow is Tuesday. But I'm going to let you off the hook. Okay. Because what should you be doing over the next 2 weeks? Yeah, you got to get things organized. You got to get going on your studying. It doesn't have to be hours and hours every night, okay? But it does need to be some time every night, okay? Where you're getting things organized, reviewing stuff, trying problems that you haven't tried for a while, like maybe a mole equation calculation or writing out a chemical reaction, okay? Something like that, okay? Having a look at those, seeing what kind of things you're going to need to ask about, okay? When it comes time to do all that.